Okay. Don't know what happened to the rest. Right, so yeah, I'm going to continue on the volume integral, in fact. That means the integration under a surface to find the volume of the space that is underneath a surface function, right, and above the xy plane, certainly, okay? Yeah, so you can see that the volume under a surface, right, can be expressed as a double integral. Okay, so the double integral, as we have gone through yesterday, it is a first integral in the x direction, for example. Of course, you can swap the order, but you can choose to integrate with respect to x first, and then followed by integration with respect to y. So the concept of this is when you integrate, when you have the inner integral with respect to x, right, then actually what you are doing is that you are finding some area that is dependent on the y coordinate. Okay, the logical reason is that, right, you see, if you integrate this function f respect to x, then you sub in the lower x limit and the upper x limit, right, then the x terms will just disappear. So if the x terms disappear, then this integral becomes giving you eventually a function in y, a function of y. All right, okay? So therefore, in this respect, right, it is actually finding you the area of y as being represented by the graph here. So you can see that it is area of y, right? And this makes sense because at different y values, you have different areas, as you can see, as you can visualize, right? If you take different slices of a bread, let's say you buy a loaf of bread, right? It is possible that you slice at different coordinate of the bread or y coordinate of the bread, you can get different areas of the bread. Okay, of course, I'm not talking about the gardenia type lah. Okay, I'm not talking about the traditional type, right? Where there is the function, so the surface of the top part of the bread is not like a flat surface. Okay, yeah. So therefore, if you understand this, then you take the area times the thickness dy, then you just get like a slice of bread, correct? You get a volume of a slice of bread. Then subsequently, if you sum up all the slices of bread in the y direction, then you get a whole loaf lah. So you get a volume of the whole loaf of bread. Okay? So certainly, you can also do with respect to y first, as you will see later on. But firstly, I want to just demonstrate this integration procedure. So we have the function here given as 3 minus y. Okay, so you can see this is generalized as f of xy, right? That means you can see that the function has no x inside, but that means x can be any number, any value. Okay, so if I were to draw this, it's not difficult to draw. So you can just sketch this first. So you can see this guy, right? It's like, so you draw your x, y input plane, and then this is your z equals to f of xy. So 3 minus y. So 3 minus y is that when y equals to 0, z equals to 3 . So it must be 3 here. Can okay? That means at y equals to 3, f will be 0. So therefore, you have something like that. Okay, and then z, you can see, equals to 3 minus y, and there is no x. So I mentioned that x can be anything, right? So which means you can just extend this line, right, into a plane. You see? So this is actually your f of xy equals to 3 minus y plane. And certainly you get a plane because it's linear in y. Is that right? Okay? So, therefore, now you are supposed to find the volume from 0, 3 in x to 0, 2 in y. Okay? So, which means 0, 3 is like at our origin, and then when x equals to 3. So, this part. And then this will be 0, 2, right? So, 0, 2. So, this is 3. So, actually, you want only up till 2 here. That means y will be 0 to 2. Okay? So, you can imagine actually what is this volume? This volume is like a trapezium. If I draw, right, you can see that it looks something like that. You see? So actually you want the trapezium volume, the trapezoidal volume. Okay, of course we can use like simple volume formulas to find the volume, but of course we're trying to demonstrate the usage of integration here to find the same volume. Okay, yeah, so therefore the volume, right, is just given by double integral. Okay, so I can do with respect to x first, right? So we have 3 minus y, which is your function. Okay, then let's do with respect to x first. Okay, follow the example in the earlier slide, or the concept in the earlier slide. That means this part, right, must be from what? X equals to 0, x equals to 0, to x equals to 3. Okay, because you integrate with respect to x first, right? So the limits must be for x first. Then subsequently, there's an outer integral. So then the outer integral, right, we integrate with respect to y. Okay, so it means this will be y equals to 0 to y equals to 2. Is that all right? Okay, so really this is just this guy, right, applied to the function that is given. So what you do is that you compute the inner integral first. Okay, maybe I change that to blue color. So therefore, what we can do is, so just integrate the inner function first, the blue color function. So therefore, this is going to give us integrate respect to x. So you treat 3 minus y as like a constant, okay? So guess what? You're just going to keep the whole 3 minus y because it's like a constant. And then x. Because you integrate a constant with respect to x, then you get kx lor. Then after that, sub in the limits. So these limits, keep in mind that they are for x. Don't go and sub in the y. Okay, because now you got two variables, you have to be extra careful here. Okay, so therefore, then this is really giving me, so the evaluation is quite straightforward for this expression. So this guy will be just 3 minus 0, which is giving me 3. Can okay, just put a 3 because x, sub in 3 and minus 0, so you get this. Okay, so then of course, if you want, right, you can factorize this 3 out. So if you factorize out the 3, then you have just an integration with respect to y now. Okay, so integral from 0 to 2, then this is 3 minus y dy. Is that right? Can Okay, then now this is trivial because this guy is going to give me 3. Then I have 3y minus y squared over 2. So that's just integrating with respect to y. Then subsequently you sub in the limits 0 to 2. Okay? So therefore that will be giving us the answer then. So you can see that if you sub in 2, then you just get 3 times 2, which is 6, minus 2 squared, which is 4, divide by 2, then minus a 0. Okay? Because sub in 0 is just 0. Can So therefore this is really 6 minus 2, which is 4, 4 times 3, which will give you 12. So the volume is just 12. Any questions? Okay? Can So you get 12 like units cubed for the volume, if you will. Okay, so if you try to verify the volume using a formula, actually the volume are just very simple. You can see that, right, this block, right, is represented by a trapezium on the side, correct or not? So basically, you just take the area of this trapezium, the area of this green trapezium, multiply by the width. So you can see that, right? If I use the volume formula, I can get the answer also. Okay, so let me write. Volume is equivalent to, so the area of the trapezium, right, must be half AB times height. So it's going to be what? Half. So what's the height here? The height here is 3, correct or not? So half 3 plus this height here. So this height here, right, is actually 1. Okay, so this height is 3, This height is 3. But this height is 1, okay? Then after that, you multiply by the width, which is in this case 2. So this is the area of the green trapezium. Then after you just multiply by the width, which is 3, then times 3. Any objections? So the answer will be 12, right? Because it's 2 times, okay, the half will cancel off this. Then it's a 4. 4 times 3 is 12. You know the area of a trapezium? Area of trapezium is half AB times height lah. So you can see the height is 3 here. Then this is going to be 1. Why is this 1? Because your y is 2 ma, 3 minus 2. So therefore F will be 1 here. Yes. Yeah. Oh yes. So when you integrate with respect to x, right, you have to treat the terms, the other terms as constants. So let me write. This 3 minus y is treated as constant. Treated as constant when integrating with respect to x. Is that right? So this is always the case. If you integrate with respect to x, right, you treat all other variables as constants. It's like just like differentiation. Any questions? Any other questions? Z equals to 3. Then see, this is z equals to 3. Then this is z. And then it's the same level line or level curve as, this is 3. So this is 1. Okay, because the width here is 3. This width is 3. This width is 3. Any other questions? I mean, the visualization is important for the understanding of actually what the double integral is trying to find. It's trying to find a volume. Yes? Okay, 3 plus 1. So a trapezium, let's say looking something like that. Okay, so this is B. This is, okay. Hold on. Trapezium. So this one is A, this one is B, this one is H. So the area of trapezium, half A plus B times H. So this is the area of the trapezium. If I didn't remember wrongly, this one you prove in your integration tutorial. But I didn't go through, you're supposed to do it yourself. Is that alright? So the area here, right, is half AB plus H. Oh, sorry, half A plus B times H. Okay, this one just for verification. Of course, the integration will give you the volume. Okay, but truth is, right, you can only use all these simple formulas if your shape is simple. If I give you a curved surface, then of course you cannot use such formulas. You have to resort to integration. Integration is the so-called most fundamental method for finding all these areas and volumes and whatnot. Okay, yeah, so as I mentioned, you can also sort the order of integration. So that means that you do with respect to y first, then you do with respect to x. And then what is the meaning here is that, right, after you integrate with respect to y, you get the area that is dependent on x. So you get like A of x. Okay, so you can see the orientation change of the slice of bread. So previously, right, it's like in this orientation. Okay, that means the slice, right, is like along the x-axis because you integrate with respect to x first. Then this guy, right, the slice is along the y-axis because you integrate with respect to y first. Observe that, okay? But then this is just like doing the same thing to find the same volume. Just that, right, you are now summing up the slabs in a different direction, that's all. Understand? Yeah, so if you were to do the integration in the last example with respect to y first, right, then actually you get the same answer. So volume is double integral, right? So you do 3 minus y with respect to y first, then with respect to x. So you must understand that if you do respect to y, you must change the limits as well. So take note that the y is from 0 to 2, x is from 0 to 3. So therefore in this respect, this will be 0 to 2 first, then followed by 0 to 3 in x. Okay, so if I change the color, you'll be able to observe this more clearly. Okay, so x will be 0 to 3, y will be 0 to 2. Okay, so if you integrate this, then you get the same exact answer. So this guy, right, is going to give you 3y minus y square, then evaluated from 0 to 2. Oh, sorry, my y square over 2. Y square must over 2. Okay, right. So therefore this will give me an integration which is 3 times 2, so which is 6. So it's going to be 6 minus 4 over 2. Okay, yeah? I sub in, then minus 0, of course. Then this whole thing, right, you have to integrate respect to x, okay? But this is really just 6 minus 2, what? So that means you are integrating 4 respect to x. Then if you are integrating 4 respect to x, you just get 4x, oh? Then after that, you sub in limits from 0 to 3, you are still going to get 12, which is obviously the same as earlier, because you are finding the same volume. You are just integrating in a different order, that's all. So it must give you the same volume. True, correct. So actually, which order of integration you can choose, right, is up to the problem and also your feeling that which direction or which order that you integrate first is easier. Yeah, go lah. Okay? Okay. So actually the observation that the order of the integrals can be switched is called Fubini's theorem, right? So what Fubini says is that, right, actually I don't care how you integrate. I don't care how you integrate. As long as the region R is the same, right? You can integrate with respect to x first, with respect to y first, or with respect to other things first, right? As long as the integration region R is the same, the function is also the same, then you are definitely going to get the same result, regardless of how you integrate. Okay? Yeah. So in the next example, we're going to see that one order of integration will be preferred over the other. Okay? So if you look at this function, so you can see this function is kind of a curved surface, right? Which is denoted by x sine xy. Okay? So if you integrate x sine xy with respect to x first, can or not? Can, no problem. But you need integration by parts, ma. You see, if you do this first, then you need integration by parts. Need integration by parts. Okay? Which means that actually I can swap, right? If I swap, then I don't need to do integration by parts. Because if I integrate with respect to y first, I don't have two functions of y multiplied together, ma. So therefore, the trick to make this integration easier is simply to swap. So integrate from 0 to pi x sine xy. Oh, sorry. Hold on. So let me write. Okay, let me write the whole thing in blue. So 1 to 2, right? X sine xy. Then dy dx. Cannot. So now you do with respect to y first. Do with respect to y first. You do with respect to y first, then this one is just a function of y. X is a constant. Okay? So therefore, outer integral keep first. And then when you integrate x sine xy, x is like a constant, so just put down. Okay? Then this sine xy, right, integrate with respect to y, you're going to get minus cosine, right? But when you integrate xy with respect to y, you're going to get 1 over x. 1 over x, the reverse chain rule, and then you get a minus cosine xy. Okay? So therefore, because you integrated respect to y, so that means you must sub in the limits for y. So you'll be y equals to 1, just to be clear, y equals to 2. Then dx. Cannot. Okay? So you can observe that if you differentiate cosine, you're going to get minus sine. Then minus minus, right? There's a minus here, so therefore you get a sine term here. So that's correct. Alright? So then you can see that, right, the x and x can cancel. So this x and this x can cancel. So that makes the whole integrand easier. So then you integrate respect, you can straight away, okay, wait. Let me sub in the values first, sub in the limits. Okay, so this will be what? Minus cosine, so I put a minus outside lah. Okay, cosine of 2x minus cosine of x. Can because you sub in the limits where y equals to 1 and 2. So therefore from here you just getting minus integration of straight away integrate. Yes. How do I get what? Minus 1 over x. Okay, because you integrate cosine x, you integrate sine xy, correct or not? Sine xy with respect to y, correct? So the reverse chain rule will give you 1 over x, right? The reverse chain rule is going to give you 1 over x. So if you integrate sine xy with respect to y, of course you can use your substitution. Let u equals to xy. Then du equals to x dy. So dy equals to x du, 1 over x du. So therefore this guy becomes integral of sine u, then dy is 1 over x du. So that's why you get a 1 over x. This 1 over x here. Then when you integrate sine, you get minus cosine. Isn't that correct? So therefore this will be 1 over x minus cosine u. Okay, plus c lah, right? Then this is just minus cosine xy ma. Yes, x is a constant when you integrate respect to y. Okay, so this one you have to do quite a bit of practice to get used to it. Any other questions? Yeah, so the volume here is a 0 because you can see the graph. Some parts of the surface is above the xy plane. Some parts of the surface is below the xy plane. So that means that the volume for those above will cancel off exactly with those below. So the volume cancels off, just like the area can cancel off also. Okay? Yep. Right. Yeah, so of course you can do integration by parts, but it's going to give you more tedious operations. Okay, so now we are going to up the notch a little bit on the region of integration. So far, right, you have seen that regions that are rectangular. Okay, so for example, like this one that we showed here, right, you can see that the region R of integration is rectangular. So x limits are constants, y limits are constants. Okay, so when that is the case, actually you can swap the order of integration by just directly swapping the limits. Okay, but when the region of integration R is not some rectangle, then you have to be careful. Okay, so I'm going to show you how this is being applied. Okay, now let's say the region of integration is given by the region that is trapped within y equals to x squared to y equals to x. Okay, so this is just an example. Okay, see so this is a region R that is between y equals to x squared to y equals to x. Okay, so let me show you the 3D picture of how like a volume like that, right, might look like. Okay, so of course this is just looking at the xy plane, right? You actually have a 3D volume. So if you draw the xy plane and then you also draw some function f of xy. So the f of xy here is going to be the height as usual. So you can see that this region R, right, might be looking something like that. Right now, this is your region R. So let me shade. Okay, this is the region of integration R. Okay, right? Okay. So but then you need to project this to 3D because you are finding the volume. Right? So when you project to 3D, right, maybe the fella looks something like that. It's like a, I don't know, like a slab of something lah. Okay, does this look, okay, maybe it's not very 3D, but I think you get the idea. Okay, yeah, it looks like an airfoil, exactly. Wow, you're good. Okay, so this is like a 3-dimensional thing. Right, of course the surface function here, I draw a bit simple lah. Okay, it can be like wavy one also. Okay, so therefore if you look at the region R here, okay, how do we evaluate the region R? Now, as I have mentioned before, the region R is actually in the limits. Okay, in the limits. So you see, if you integrate respect to y first, let's say you integrate respect to y first. Okay, now you are going to integrate respect to y from y equals to what to y equals to what? You must go from y equals to x squared all the way to y equals to x what? Correct or not? Integrate from y equals to x squared to y equals to x. You can see the lower limit is x squared. upper limit is x, and you are integrating with respect to y. So therefore, right, what we say here is that you are using the vertical slab or vertical element. Okay, then after that you integrate with respect to x, but x has to go from where to where? Because you are looking for the region R that is between the intersection points of the two curves. So therefore you have the intersection at x equals to 0, and the other one is the intersection at x equals to 1. Okay, of course you can find for the intersection easily by just letting x squared equals to x. Okay, then you can solve x equals to 0 and 1 respectively, which are the x coordinates of the intersection points. Okay, so therefore, if you want to find this volume here, right, then you just integrate respect to x from 0 to 1. Okay, so the outer integral is like you are summing up all the slabs, like you sum up the first slab to the second slab, to the third slab, to the fourth slab, and so on and so forth. So this one is like the outer integral. The inner integral is to give you the slab, one slab, the volume of one slab only. Okay, so let me write, this one is like the outer integral, sum up all vertical slabs. Can Okay, so you sum until the last slab at x equals to 1. Is that right? Okay, so what's the difference here? Actually, the difference is just that, right? Instead of constants for your limits, you can have some limits being functions. You see? Any questions? Actually, the same concept applies, but just that limits can be functions. Okay? Now, take note that whatever the limit there are functions, right, has to be at the inner integral. Outer integral must be constants. Makes sense what? Because you want to find volume. You want to find volume, which is a number, for example. The outermost integral must be constants, the limits. Right? Because if you sub in a constant limit, then you get a constant. Okay? So, you can also switch the order of integration according to Fubini. As long as the region R is the same, right? I don't care how you integrate. Okay, but now, check this out. What happens if you integrate respect to x first? Now, if you integrate respect to x first, means you are taking the horizontal slab. You are using the horizontal slab, summing up horizontal slabs instead of vertical slabs. However, now when you sum up horizontal slabs, right? Now look at the limit. The limit is not just a simple swap. You must understand that at this point, y equals to x means x equals to y. So the lower limit of x must be x equals to y. Okay? What about the upper limit of x? Now, because the orange curve, right, is given by y equals to x squared. So this curve is y equals to x squared. Now, if y equals to x squared, you take root both sides, right? You are going to get x equals to root y. So therefore, the upper limit must be x equals to root y. If you are integrating with respect to x first, right, it's below y equals to x. Because the function here is 0 to 1. I mean, the bound here is 0 to 1. The interval here is 0 to 1. So let's say you get 0.5 here. Let's say, for example, let's say this is 0.5. Okay? Oh, sorry. Let's say the x is 0.5. Then let's say you 0.5 square is 0.25. Then this is 0.5. So 0.25 is below 0.5. Okay? So now you see, this is a lower limit, right? That is having a lower y value as compared to the higher limit, which is a higher y value. So therefore, it must always be lower y to higher y. Okay? And this is making sense from the graph as well. Can you see? Then you just make use of this understanding and apply to the x direction as well. So this one must be what? Must be lower x to higher x what? So x equals to y. Why is this x equals to y? Because the green line is y equals to x. This green line is y equals to x, y equals to x is just x equals to y, it's the same thing. Correct. It's two separate lines or two separate curves that form the region R. Correct. You can just look at the graph also lah. So we must go from lower limit in x to the higher limit in x. Just lower value in x. What you can see what? This one is higher limit. I mean higher value in x. What must go from low to high. Can? Okay. So now if you look at this is one slab which is given by the inner integral. Then the outer integral do what? Outer integral is going to sum up from y equals to 0. So sum to the next slab. Then sum to the next slab. So you can see it is summing. Summing all the blue slabs all the way until the last slab at y equals to 1. Is that alright? So this is what the outer integral is doing. Sum up all horizontal slab. Any part not clear? So you can see the functions are different. The functions is no longer the same two functions in this case, if you were integrating respect to y first. Okay, you have to convert the functions in terms of x equals to some function of y. Then you can integrate respect to x first. Okay, but clearly the region R is still the same. Any objections? Okay, so we're going to demonstrate this idea using an example. Can Okay. Yeah, so the area bounded by the region R can be found by area equals to integral 1 dA. Okay, why is that so? Because if you are integrating a height of 1, so it means to say that, right, the volume is just area times 1. Let's say you can see this is the region R, so let me draw. Okay, let me try to draw 3D. So you can see that this is the area A, right? I want to find this area A now. So I can say that, oh, the height is just 1. The height is just 1. Okay, wait, not very nice. I want to draw again. Can you see? So this is like a 3D film. Then this height, right, is 1. So what is the volume? So volume must be area times 1, because it's the base area times height. That means this is also equivalent to area. So the volume equals to the area numerically. Okay, that means the value, right? So therefore, if you integrate double integral 1 over the area of region R, then you're just finding the total area, lor. Can Okay? Double integral. So this is double integral over region R. Okay, so let us find the area now. So area A, right, as I mentioned, is, so I'm going to do with respect to, let's say, vertical first. Okay? So vertical first, right, means y equals to x squared. So y equals to x squared to y equals to x. Then I just do a 1. Then I have dy dx. Then x must be from 0 to 1. Okay, as explained previously. So if you integrate this, right, you can see that. So integrate 1, that means you get y, right? So you'll be y, then you sub in x squared and x respectively. So just integrate 0 to 1. Then this will be x minus x squared dx. Then now you have x squared over 2 minus x cubed over 3. Then you're going to sub in the limits from 0 to 1. And therefore, you're just getting half minus 1/3. So half minus 1/3 is just 1 over 6. Is that all right? Okay, so I integrated with respect to y first. So which means that, right, actually this integration, I'm using the vertical element. Hold on, let me see what color I use. Okay, I use purple color. Okay, maybe I put purple color here. Doesn't look like purple. Looks like pink. Doesn't matter. So I'm using this, summing up these elements. Yeah. No, it can be any function. If I have a function here, then just integrate respect to y and x accordingly. It's just that now the function is a 1. It's a constant function. It means the height is constant at 1. Can? Okay, so then what about if I were to integrate? If I were to integrate with respect to x first. With respect to x first, right? That means I use the horizontal element. So I use the blue element here. Okay? So what will be the result? The result is certainly going to be also 1 over 6. So area is double integral. Then 1, now I do dx first, then dy. Okay, but lower limit is x equals to y, correct not? X equals to y. Then upper limit, just now we evaluated it, is x equals to root y. Okay, because y equals to x squared. So now x equals to root y. So therefore now, right, of course, the y limits will be from 0 to 1 as well. Okay, so now I integrate the inner integral first. So it's just going to be x, then sub in y and root y accordingly. Then after that, I have root y minus y dy. So now I integrate, I get, so root y is really just y to the power of half. So I get, obviously I should get y to the power of 3 over 2. So y to the power of 3 over 2, right? I'm going to have a 2 over 3. Okay? So then minus y squared over 2. Then I sub in 0 and 1. Okay? For the limits. So therefore, if you evaluate this, you can see that this guy is going to give me 2/3 minus half. Is that right? Okay? So 2/3 minus half is actually 4 over 6 minus 3 over 6, right? So therefore, it is also 1/6. Is that right? Okay, which is expected lah, because it's the same area of region R. So both areas has to be the same. You are finding the same area of region R. Any questions? No difference in this respect. Because the function is always just 1. In this case, the function is 1, right? So there's no function consideration. There's no consideration of the function, like which one you integrate is easier. So if you ask me, I feel both is about the same. Yeah, so you can do it any way you prefer. Okay, unless the question states that, oh, you have to do it in a certain order, then you follow lor. Right? If it didn't state, then you can choose any you prefer. Can? Right, so this will be for general regions. Okay, so now we look at another example. So let's say a prism has a triangular base that is bounded by the lines y equals to 0, y equals to x, and x equals to 1, and a top surface that is given by this function below. So evaluate the volume by both orders of integration and sketch the region of integration. Okay, important, you must always sketch the region of integration. Okay, because it will be giving you a clearer picture of what the limits should be. Now you see y equals to 0, obviously just means the x-axis. Then y equals to x, is just this line, y equals to x. Then x equals to 1, right, it's just this line, x equals to 1. Okay, it's a vertical line. So therefore, x equals to 1, y equals to x, and y equals to 0 will be this triangle. So this is my region R. Any objections? So this thing is going to give me region R, which is given by this triangular region here. Okay, so top surface is just this function, is a plane. Okay, so evaluate its volume by both orders of integration. So now, what you want to use first? Let's say we do with respect to y first. Let's do with respect to y first. Okay, so respect to y, let me draw the element. I always like to draw the element because it gives me a very visual understanding, right, of what my limits should be. Okay, so lower limit must be what? Lower limit must be y equals to 0, ma. Correct or not? X-axis lah. Upper limit must be what? Upper limit must be y equals to x, what? Okay? So that means the inner integral, I just integrate from y equals to 0 to y equals to x. Then the function is given. The one cannot change. Then this one do respect to y. Then after that, you will sum up all this vertical element from what? From x equals to 0 to x equals to 1, ma. That's specified by the region R already. So therefore, this will be from 0 to 1, and this is in x. Is that all right? So this will be giving you the volume under this flat surface. Okay? Yeah, so therefore now you just have to perform this integration. So let's do it together. Okay, so now this integral, right? Integrate with respect to y first. So therefore, obviously, you're going to get 3y minus xy minus y squared over 2. Can? Okay? Then after this whole bunch, right, you have to fit in the y equals to 0 and y equals to x limits. Then you have your dx outside. So integrate 0 to 1. So this guy, right, sub in the limits. So sub in the limits, you're going to get what? 3x, correct? Because y equals to x. So 3x minus x squared. Then minus x squared over 2. Okay? Then minus 0, because all y's are 0, right? So just minus 0 lah, for clarity. And then this is dx. dx. Okay, so therefore if I simplify this expression, you are really just integrating 3x minus 3 over 2x squared. Is that right? So if you want, you can factorize out the 3, okay, but I can just integrate directly. So therefore this becomes 3x squared over 2 minus half x cubed. Then I plug in the limits 0 to 1. Is that right? Okay. Then after I sub in the 1 and 0, I'm just going to get my 3 over 2 minus half. Can I? Okay, and of course minus 0 lah, if I'm subbing 0. Just 1 oh. Minus 0 because you sub in the 0 inside. Because lower limit you must sub in also, right? Then it's just 0 minus 0. Oh. So this one minus 0. This you sub in 0, right? You're going to get this 0. Minus 0 lah, but I just put a minus 0 there for clarity. Cannot. Okay, so if you were to do it using the horizontal element, then it must be from x equals to y to x equals to 1 ma. This point is x equals to 1. X equals to 1 right there. Okay. Then the lower x point, right, is actually x equals to, okay, wait, let me just put it here. Okay, this one is x equals to y. But this point is x equals to y. Okay, so using the other order of integration, right, it must be integrate, then integrate from x equals to y to x equals to 1. Then it's the same function. This one function cannot change one, given. But you do dx first, then followed by dy. Okay, so y must be what? Y must be from y equals to 0 to y equals to 1. Okay, so you see, so I draw bigger a bit. So you can see that this point is what? Y equals to 1, what? Correct not? Okay, so x equals to 1, y equals to 1 ma. So y equals to 0 to y equals to 1 because you sum up all the horizontal slabs. Okay, so maybe just to be clear, y equals to 0 to y equals to 1. Okay, so this one I don't waste time doing lah. Okay, basically it's going to be giving you the same answer if you were to integrate accordingly. You're going to get 1. You can go and try because the integration is straightforward. Any questions? So basically, it's just like, you know, visualizing what your region is given the boundaries or constraints. Then after that, you just draw some element and then visualize, like, you know, where is your lower limit and upper limit. Then you sub inside the integral. Okay, I must tell you that, right, this writing down this integral correctly with the correct limits, this one you will score substantial marks already. Let's say 10 marks question. You just write down this thing. I think you get 4 marks already. I repeat again. Really. Let's say I give you, find the volume of blah, 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 right? Some region R, blah, 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 blah. Okay, you just write down this thing. Let's say it's a 10 marks question. You just write that thing down correctly. With the integrand correct, the limits all correct, right? You get 4 marks. That means you pass already. 4 or 10 is pass, what? Okay, never mind. So, yeah. So, you write down that correct integral. That means you know what you are doing. The rest is just arithmetic, meaning to say just performing integration. That one does the boring stuff. Yeah. Then will be quite disastrous. Because if you cannot write down this expression correctly, then I don't know whether you know what you are finding or not. Or you anyhow just plug in some functions or what. Then it's very severe. This thing must be correct. Then the rest, if you get it correct, then of course you will get the accumulated marks. Of course. That's why that's the difficulty of multiple integrals. Can be 3D one. Well, you need practice. If you have enough practice. Okay? Can Okay, so next part. By the way, you guys need a break or not? No response? No response, then I continue. Continue, Okay. So just now, actually, in our examples, right, we evaluated a double integral with respect to x and y, So this means the double integral is integrated in the Cartesian coordinate system. Okay, because xy or xyz, if you do triple integrals later on. So which means that actually we can choose other coordinate systems to do our integration as well, and that would be advantageous for certain regions and for certain functions. So now you see, okay, before we talk about the polar coordinate system, now if you look at this first expression, okay, so now I'm trying to find a volume, right? And now I take the height times dA, right? So this one I mentioned, this dA is really just the area of each block, of each infinitesimally thin block. Okay, so you take the area here, multiply by the height, which is f of xy, you get the infinitesimal volume. Okay, so in this case, right, we call it a volume element. Because you sum up all the volumes of all elements, right, then you get the total volume, correct or not? But in this case, right, we call this a volume element. Volume element. Okay, so this is just some jargon, right, but it's useful for defining other elements. So now, if you take this dA and you expand it into the Cartesian coordinate system, which is dx dy, right, like here, then you are having this volume element in the Cartesian coordinate system. Okay, so it's a Cartesian volume element. Can Okay, so now if you understand that, right, then we ask the logical question. What happens if we switch to a different coordinate system, let's say the polar coordinate system? Is there such a volume element in other coordinate systems or not? The answer is yes. Okay? So now let's look at the element, the area element that is in the polar coordinate system. Because we know that polar coordinate, right, is r and theta. So let's say this point. So this point, right, I mean the coordinate is xy in Cartesian, but this one we mentioned before. The same point, I can give you the position by defining r and theta. So what is theta? Theta is this angle. I give you the angle, I give you the radius from the origin, you can tell me the position. You can identify the position of a point. Okay? So therefore, I have r and theta. Now you see, what is the element here? Similar to the Cartesian element, you have the directions x and y, right? X and y. And you want a small change in x, so called dx. Then you want a small change in y called dy. So dx times dy is dA. Okay? So in the polar element, you want something like dr and d theta involved. Because Cartesian, your directions are what? Your directions are x. Okay, but in polar, what are your directions? dr and d theta. So what is dr? Change in r. You see, this is in the r direction, correct or not? Okay, the r direction. Therefore, this dr is change in r. Then what about d theta? But d theta, you must understand that it's an angle. It's an angle. So we ask, what is the length of this element here? The length must be r times d theta, s equals to r theta. Okay? And then, what is the length here? The length here must be r plus dr. Because the radius now is r plus dr, this long. Right? And then multiply by d theta. So you get the arc length here. Can see, okay? But because your dr is very small, because dr is like go to 0, that means the element here, right, is like shrinking to a very small area. So dr is very small. So if this dr is very small, right, then r plus dr is going to approximate or approach r d theta. Okay? That means this r plus dr, right, is very close to just r. Because dr is very small. So let me write, okay, this dr is approaching 0. Okay? dr approaches 0. Because it's very small. It's not exactly 0, or else you get no element. Okay? It approaches 0. So therefore, r plus dr must approach r. Okay, right? So then we ask the logical question, then what is the area of this element dA? Now it's just length times breadth. So it's just dr times r d theta. Can you see? R d theta times dr. Just length times breadth. Okay? So therefore, the area is r d theta. Is that right? So this is like dx dy in Cartesian. In Cartesian, it's very easy to visualize. The element, right, the area here is dA equals to dx times dy. It's just length times breadth also lah. But because polar element, right, it's not like a nice rectangle. It looks like a arc, like a sector or section of a circle, if you will. Okay? But then, because dr is very short, and d theta is also very small, a very small change in angle. So which means actually this dA, this shape, right, is going to approach, this shape is going to approach more like a rectangle as well, right? Correct not? Because you can see this is r d theta. This edge is r d theta, the length. Then the upper edge here, right, is also approaching r d theta. Then the two sides are dr ma. So therefore this area dA must be length times breadth what? R d theta times dr what? Is that right? So therefore, what I'm trying to say here, right, is that now you have evaluated the expression for dA. So now the double integral in polar chords is going to be just replacing the dA by r d theta. So now your function, right, must be a function of r theta instead of a function of xy. Is that all right? Yes. Correct. Very good. This r d theta, because your d theta like very small, right? So you shrink until it's like the sector is so thin. So it's so thin that it approximates a rectangle or square. Okay, this one will require some visualization lah, right? But the important part is not this one. The important part, right, is that you can always replace this dA in terms of the coordinate system that you are integrating in. So this dA can be replaced by this, and then now because you change your coordinate to from Cartesian to polar, right? So now the function must be converted from f of xy to f of r theta. Is that all right? Yeah. So then maybe let us go through this exercise together. Now, what is the polar element that is representing the volume under some surface? What is the polar element for the volume? Because this one is the polar element for the area. Okay, then what about the volume? Actually, the volume is just extending by one more dimension. Okay, so I can draw. So you see, if I have a surface that maybe looks something like that. So this is my surface. So now I want to find the volume under this surface by looking at one polar element. So the polar element looks like that, right? Because the polar element, I draw a little bit bigger. Okay, so this is my polar element in 3D that is on the plane. Can you see? Okay, so this one is my r d theta, and this is my dr. Okay, wait, I put a dr on the other side. Okay, so then this function of r theta must be the height, the height to the surface. So this must be f of r theta. Okay, no, it must be the height. So therefore, if you take area times height, what do you have? You have volume, no? So the volume, okay, let me draw the volume. The volume must be something like that. Okay, wait. Let me just try my best here. Can you see? It's like an elongated piece of cheese. Can you see? This one. This is my volume element. Polar volume element, which is f at r theta, the height, times r dr d theta. This one is your area dA. Cannot? Correct. I extrude the sector out. Then it becomes like polar volume element, no? Which is analogous to the Cartesian volume element. Cartesian volume element is just with a base area that is looking like a square. But this one looks like a sector. But look like square or sector doesn't matter lah. Eventually you just sum up all the elements, you get the total volume, that's all. Correct. What do you mean? No, you just take this area, right, dA times height. So then become volume already. So this is like the base area. So this one is your dA. So dA extrude upwards to the surface. Is that okay? Yeah. Okay, maybe I answer your question later. Okay? So now we move on first. So now, okay, so how do you do the double integral in polar coordinates? So basically, you need to identify the limits for r and theta now. Okay, you need to identify the limits for r and theta instead of x and y earlier on. Because when you integrate respect to x and y, obviously you need to put in the limits for your x and y respectively. Okay, and the same goes with r and theta. You have to find the limits in terms of r and theta in order for you to perform the integration. Okay, so let's say the function is f equals to x squared plus y squared. Okay, and the region R is this semi-disk. Okay, you can see it's within the semicircle lah. Okay, so it's called a semi-disk. Can see the region R, right? It's a unit semi-disk, right? So therefore, what are the limits? Can see, very simple. Limits for R will be from R equals to 0 to R equals to 1. And then, because it's in the upper half of the plane, so therefore the limits for theta must be from theta equals to 0 to theta equals to pi. Okay? So you can see my double integral. X squared plus y squared in polar coordinates is just r squared. Okay? Then I have my dA, which is my r dr d theta. This dA, right, is my r dr d theta. Okay? Then the function x squared plus y squared is just r squared. Change to polar coordinates, which is this r squared here. Can? So therefore, I put in the limits for r and theta, as mentioned, r 0 to 1, theta will be 0 to pi. Okay, so eventually, I'm just integrating r cubed. I'm just integrating r cubed with respect to r and with respect to theta. Okay, so from this part to this part, any questions? Basically, I just converted the x and y function, right? The x function of x and y to a function of r and theta. So actually, this is like g, some function, right, of r comma theta, which is equivalent to the function of x, r comma theta, comma y, r comma theta. Okay? Because what's x? X actually is r squared cosine square theta sorry, x is r cosine theta. Okay, so you can see this guy is actually what? X squared plus y squared, correct or not? But what is x? X is r cosine theta, but whole thing square. So it's actually r cos square theta plus r square sine square theta. Okay, then sine square plus cosine square is 1 what? So therefore it's r square. You see? This is the r square that we are talking about after you have converted from Cartesian to polar. Okay? Then the dA will be just r dr d theta. Any questions? Okay. So now, how do you integrate this? Basically just integrate r cubed dr. I mean, very easy. Integrate r cubed, right? Just r to the power of 4 divided by 4. Then start in limits. Okay, but the question you have here, right, is, how come this integration with respect to theta can like factorize out? Meaning to say, right, can be like separated, the two integrals. Okay, now the truth is, right, you can separate whenever your variables in r and your variables in theta, right, can be so-called performed independently in terms of the integration. Okay, so I'm going to prove this to you. But this only happens, right, when your limits are constants. Okay, so because this integration will be faster to do. Now, see, okay, integrate. So now you do, let's say, function of r times another function of theta. Okay, then you have dr d theta. Let's say you have something like that. Okay, which is similar to what we have here lah. It's just that the function of theta here is 1. Okay, because it says r cubed, correct not? So it's just function of r. So what's the function of theta? Like 1, no? Okay, like you times 1. So now, observe this. So if you have function of r times function of theta, then you integrate respect to r. So let's say this is constant. must be like constant. So it's like R1 to R2 lah. R1 to R2. Then this one is like theta 1 to theta 2. Okay, see this expression. Okay, so now if I integrate this expression respect to R first, then it must be the outer integral remain. Then this inner integral, so I treat g of theta as a constant, correct or not? Now I integrate this small f of r. So I get big F of r times g of theta. Then I got to evaluate R1 to R2. Then I have a d theta outside. Okay, then, but this one, right, is really just outer integral. Then this is f of R2 minus big F of R1. So this whole thing multiplied by your g of theta d theta. Okay? But this is just a constant. This is like a constant. Why constant? Because you sub in the R1 and R2, which are constants, what? Correct or not? So f of R2 minus f of R1 is just constant. Now you integrate respect to theta now. So guess what? You're just having the same constant because theta 2 is at the upper limit. Correct or not? Correct, right? But then you look at these two expressions like that, isn't this the same thing as if you were to integrate f and g separately? So this is the same as integrate R1 to R2 small f of r dr times integrate g of theta d theta from theta 1 to theta 2. Also that, okay? So what you're trying to show here is, right, this is the same as this. Okay? So, which means, right, if your limits are constants, so this only works, this whole thing only works. If you perform this integration normally, right, you have to do the integration respect to r first. Then after that, you have to do the integration respect to theta. You can't do both at the same time. But if you can make use of this, this observation here, right, then you can actually perform the integration together with respect to r and theta, right? You do it at one go. So you'll be shortening the time taken. Is that right? Okay? So therefore, this is why you can have separated integrals here. Okay? So this one I will just put like C below. C next slide. Okay? So we get pi over 4. Right? So if you integrate this, right, and you sum in the limits, you get pi over 4. Okay? So that's the volume associated with this function x squared plus y squared here. Okay? So now you see, actually this is very simple to integrate if you were to convert into polar coordinates. But if you didn't, then you are having a hard time. So this is also finding the same volume, but you do it in Cartesian coordinates. Okay, so if you do it in Cartesian coordinate, right, so actually you can see that I can choose to do with respect to y first. Can? So if I do respect to y first, right, what will be my limits? Y equals to 0 to y equals to root 1 minus x squared, because it's a region which is the semi-disk. Okay, you can see the upper limit here. Then after that, the x, right, must be from x equals to minus 1 to x equals to 1. Can you see, Okay, it's the outer limit. Right? Now, if you integrate this with respect to y, then you're going to get this. X squared y plus y cubed over 3. Correct or not? Then after that, you got to sub in the upper limit and the lower limit for y. So you can see that the y becomes this root function. So it's x squared times root 1 plus x squared. Now you need to integrate this guy. Okay, and next you need to integrate this guy. Can integrate or not? Can, but you need to make what? You need to make trigo substitutions. So you see this whole process is super tedious. Okay, but of course you can still get pi over 4 after you go through the super tedious integration process. Okay, so that is of course in contrast to if you were to do it in polar coordinates, right? You can see just a few lines you get the answer. Okay, so then of course that begs the question, when do you use polar coordinates? Now, the answer is, right, when you have this region R as part of a circle, as part of a disk. Okay, so when region R is like part of a disk, like circular shape, right, then you use polar coordinates, typically will be easier. Can Because if you observe, right, actually, in polar coordinates, this semicircle or semi-disc, the limits are constants. We always prefer constant limits. Okay, but if you look at the Cartesian version, the limits are not constants. For example, this y limit, right, is not a constant, it's a function. So therefore, it will be certainly taking a lot more time. Okay, so that will be generally the case. Okay, so now, we'll just finish today's class with this exercise because I feel that you are like dying. You are like dying, right? Okay, so just hang in there. So I'm going to finish with this exercise. No integration to do. Okay, no integration to do. Right? We just set up can already. Okay, that's why I say, right, if you can write down the correct integral, the correct double integral, right, you get a lot of marks already. Because it's not so, I would say it tests you on your understanding a lot more than just performing the integration. Okay? So now set up double integrals in both Cartesian and polar coords for the function below in the annular region that is bounded by the circle or circles of radiuses 1 and 2, and then we just evaluate the easy. Okay, so I think we just set up and then we call it a day. Okay, so what's the deal here? Okay, I always say that you should draw the region. Okay, please draw the region. Okay, let's draw the region. So the region is actually on the plane. Okay, so this will be, let's say, in the Cartesian axis. Annular region that is bounded by circles of radiuses 1 and 2. So this one easy, what? A circle of radius 1 and another circle of radius 2. So correct or not? This one is my region. Okay, wait, I'll draw it a little bit more accurately. Okay, this one's still too big. Something like that. Okay, so therefore this has to be 1 and this has to be 2. That's it. Annular region bounded by circles of radiuses 1 and 2 respectively. Cannot. This is a region R. Any objections? No objections, Okay, good. So now evaluate the double integrals in Cartesian. So let's do Cartesian first. Cartesian. Okay, so Cartesian must be what? Double integrate, right? Then the function always cannot change one. You must put in the function that is given to you. Then after that, you can do, for example, okay, let's say I do respect to y first. Then I do respect to x. So now I have to sub in limits already. Can Okay, so this is my volume. Let me write, this is the volume. Okay, so what will be the limit for y? Now the limit for y must be from this point. But what is this point? This point must be, okay. So this point must be what? Must be y equals to the lower limit, right? Because this is a circle of radius 2, correct or not? So it must be it must be minus root, because y is a negative value here. Minus root of r square, which is 2 square, which is 4, minus x square. Correct or not? That's the lower limit. Because your element must run from the lower bound all the way to the higher bound. This is your Cartesian element, vertical one. So you can see that this lower limit, right, must be from minus root 4 minus x squared all the way to this point. But this point is just y equals to positive root 4 minus x squared. So you must go to root 4 minus x squared. Agree or not? Agree, Okay, then what must be the x be? X must be from minus 2 all the way to 2. So therefore you have x equals to minus 2 all the way to 2. So in case, okay, apologies. Maybe some of you didn't understood why is it root. So you can see the outer circle here, right, is x squared plus y squared equals to 2 squared, which is 4. Okay? So therefore, if you isolate the y, then you will get the the two root expressions here. Okay? So therefore, you can get this, and you can get this. Is that right? Can Okay, so what's the problem? What's the problem? Now, the problem is that if you do this integration, right, you're going to include the inner circle also. Correct or not? Because you are summing up Correct. Because you sum out like that, you sum, so you also cover the inner, the circle in the center. You must minus away the inner circle. So you can see this one, wow, if you do in Cartesian, you will maybe like scold some not so nice languages. Okay? Yeah, so I have to minus away the integral from the inner circle. Okay, so this one must be what? Must be minus root of 1 minus x squared all the way to root 1 minus x squared. Okay, can you see? This one in Cartesian. Okay, then what about the polar one? The polar one is very easy. Polar coordinates. So volume in polar. Can see that for polar, right? What's the R? The R is going to be from R equals to 1, because this is R equals to 1. R equals to 1. Then all the way to R equals to 2. So the limits for R are constants. R equals to 2. Okay, so I just double integral again. Okay, then the function cannot change. The function is 5 minus 2x. So I have 5 minus 2. Then x is just R cosine theta. I put bracket. Then the dA, right, is actually R dr d theta. This one we discussed before already. So now what about the limit for R? Constants from R equals to 1 to R equals to 2. What? Very straight. So R equals to 1 to R equals to 2. Then the theta limit is the whole annulus. What? So 0 to 2 pi. So the outer integral is having the limits 0 to 2 pi. Theta equals to 0 to theta equals to 2 pi. Is that alright? Because you go one complete round, what? So it's the full circle. If let's say it's just the upper part, upper annulus, then you'll be 0 to pi. But this one you must sweep one complete round to cover the full annulus. So okay, sure. You see, when you integrate in the Cartesian coordinate system, right? Actually, what you do, you are like sweeping, Okay, you can visualize this as sweeping. What do I mean by sweeping? Okay, you see, one element. Okay, just look at this blue element. So then you look at your outer integral. Outer integral, you integrate from minus 2 to 2. That means, right, you are sweeping the element from minus 2, sweep all the way to 2 to cover the whole region of integration. Understand, right? Okay, now look at the integral for R. Now you are also doing a sweeping, It's just that, right, in the direction of R, you are sweeping from R equals to 1, right? Sweep outwards to R equals to 2. Correct or not? You are like sweep outwards, sweep outwards. Then after that, you need to sweep from 0 to 2 pi also. So after you sweep with respect to R, right, you are getting like a sector like that. Let me draw. So if you perform the inner integral, right, you are like getting a sector. So this is your element. Then after that, right, you sweep from 0 to 2 pi. That means you like, go one round. It's like you sum like this thing. Sum. So you sum from 0, sum all the way to 2 pi. Understand? Okay? So therefore that's the meaning. So actually when you integrate from R equals to 1 to R equals to 2, right? Actually this inner integral, you get something like that. You get something like that. Yeah, okay? So I can. So the setup is important. Then the rest, right, basically we are just going to evaluate the easier integral, which is this one. So if you evaluate this, you get 15 pi. Okay? So this one I will not do. I think I'm going to stop here. Okay? So, yeah, maybe I'll just integrate later and then just upload as the writings. Okay? But certainly, we can just integrate with respect to R and theta accordingly. Okay? It's the setup that is important. Any questions? Yes. Okay. Any other questions? If not, I'm going to stop here and let you go for your sanity break. Sanity break. I think some of you may be going crazy. Okay, that's all for today. If you have questions, can come forth and look at me. Look for me.